Ngalakin Khadijan Nyunga Boja.
Good evening, everyone. We are on the topic of load flow or power flow. We started this in the last lecture. So it's about looking at an electrical power network, right, with a number of buses, number of generators, number of loads, and then knowing the network topology, how the network is connected, how the different loads, the generators, and different bus bars are connected, knowing the network topology, and knowing some partial information about the network. In other words, we have number of nodes, and we've stated that for each of those nodes, there are 4 parameters of interest, which are active power, reactive power, voltage magnitude, and voltage angle. So those are the 4 parameters of interest for each of the nodes. Out of those 4 parameters, 2 will be known, and 2 we will not know. We will have to determine that, those 2 parameters that we don't know. And load flow is about determining those unknown parameters for each of those nodes. And once we know all the 4 parameters for each of the nodes, then we can calculate other information of interest. For example, line losses, how much, what is the voltage, magnitude, and angle at load buses, and so on. Information that is unknown to us, obviously we can determine once we've done a load flow. So in the last lecture, we actually stated that based on the information that we know about a particular node, we can actually classify that node. We have 3 classifications for each of the nodes. And those 3 classifications are, well, the node is in fact, it's referred to as a bus bar. So we have a slack bus where we know the voltage magnitude and voltage angle at that bus bar. Voltage angle by default is 0. In other bus bars, we will know the active power and reactive power consumed. That's called a load bus bar. So P and Q will be known, voltage magnitude and angle not known. and other type of bus bars where the generators are connected, we will know the power injection into the bus bar. So P will be known, voltage magnitude will be known because the terminal voltage of the generator can be maintained at some specific value. So voltage magnitude and the power injection into that bus bar will be known. So we will call that a generator bus bar. So we talked about the classifications of the different bus bars in an electrical network. We also talk about the admittance matrix. So the admittance matrix, I already spoke about that. We can generate the admittance matrix by writing Kirchhoff's current law at each of the nodes, right? By writing the Kirchhoff current law at each of the nodes, we can write all those equations in compact form using matrix notation, which is what you see there. I1, I2, I3, I4 equals the admittance matrix times the voltages of the nodes, respective nodes, V1, V2, V3, V4. We have 4 nodes in this particular network that we are looking at. So there are 4 node voltages, V1, V2, V3, V4. And obviously, we've written this equation in matrix form, which states that I1 currents, I1, I2, I3, I4 is equal to the admittance matrix Y multiplied by the voltage vector, V1, V2, V3, V4. So we have to be really, when we are looking at an equation like this, we have to be really clear what those things actually mean, what those symbols actually mean. So we know that V1, V2, V3, V4, we clearly know what they mean. They are the voltages at the various nodes. What are I1, I2, I3, I4? They are the current injection into the node. So you have a network, right? In this network, we have the inside of the network. In other words, all the connections of the network, right? All the lines that connect the different bus bars. But then you have generators connected. They are, if you like to think, they are external devices connected to the electrical network, right? Generator G1, G2, then loads will be connected at various bus bars. So for me, I would like to think those are external devices connected to those. So we can think about current injections into these nodes externally into the network. So you can see how I label I1, I2, I3, I4. So I1 is the injection externally from external into the network at node 1, and I2 likewise is the current injection into the node 2, because there are some currents that are flowing inside the network. That's not the current we are talking about. It's from external, the injection into it. So we have to be really clear. We have to understand what those I's mean and what the V's voltage vector means. So by writing Kirchhoff's current law at each of the nodes, we can arrive at that matrix equation. The currents I1, I2, I3, I4 equals the admittance matrix times the voltage vector. So then we've talked about how to actually generate the admittance matrix. I mean, it all falls off if you write the basic equations. All these become clear. But if we are not going to write the Kirchhoff's voltage equations at every node, but we just want to write this matrix equation straight away, right? We have a current vector. We know what that means. We have a voltage vector on the right-hand side of the equation. We know what it means. We need to write the admittance matrix, right? And the admittance matrix, there are elements along the diagonal, right? So there is a 1, 1 element, 2, 2 element, 3, 3 element, 4, 4 element. They are the diagonal elements. So if we are talking about the 1, 1 element, we are thinking about node 1, right? We're thinking about all the internal lines connected to node 1. So I'm thinking inside the network now, right? All the lines connected to node 1. And we are thinking about the admittances of each of those lines, and we're summing them. So Y12 is the line that connects bus bar 1 to bus bar 2. It's the admittance of the line. Y13 is the admittance of the line connecting bus bar 1 to bus bar 3. Obviously, we can consider 14, but there is no line connecting to connecting between admittance bus bar 1 and bus bar 4. So there is no Y14 element, right? So we consider all the elements, all the lines in the network, inside the network that connects to bus bar 1, and we sum all the admittances. And that's the 1,1 element. And you can do the same for 2,2 element. So we think about node 2. We think about inside the network, all the lines connecting to bus bar 2. We consider the admittances of all those lines and we sum them. We do the same thing for node 3 and node 4. Then we need to think about the off-diagonal elements. So 1, 2 is an off-diagonal element. So if I'm thinking about 1, 2, element 1, 2 in the admittance matrix, I'm thinking about bus bar 1 and bus bar 2. Makes sense, right? So and then I'm thinking about the admittance of the line connecting bus bar 1 to bus bar 2, and then I negate that, and that's the value you put in the admittance matrix, right? And you do the same for all the other off-diagonal elements. You do the same for all the other off-diagonal elements. So we know what this equation means now. We know the current vector, voltage vector, and the admittance matrix. All right. So then you would ask the question, okay, before I move on there, I said that we need to be fully aware of the notation. We need to be familiar with the notation that we are using. So notice that lowercase y12, y13, and so on, we're using lowercase, so they are the admittances of the lines connecting different bus bars, right? Now, I'm given this admittance matrix. The notation that we're going to use to represent this admittance matrix is uppercase Y, right? Uppercase Y. So, if I now refer to a particular element in that admittance matrix, 1, 1 element, uppercase Y subscript 1, 1 refers to the 1, 1 element. Uppercase Y subscript 2, 2 refers to the 2, 2 diagonal element of that matrix. Uppercase Y 1, 2 refers to minus lowercase y12. So don't confuse the uppercase symbol with the lowercase symbol. You need to be fully aware of what those different symbols mean. Okay? Because we're going to look at some equations, and in those equations there are symbols. We clearly need to know what they mean. Otherwise, you don't know how to use the equation. Right? So a few things. Firstly, how you get the equation. Next step is how do you use the equation. So you need to be fully aware of the symbols and what it means. All right. So why are we writing this equation in the first place? The current vector equals the admittance matrix times the voltage vector. Why are we doing that? The reason that we are doing that, remember at the beginning I said that for each of the nodes there are 4 parameters of interest. That is power injected, active power injected, reactive power injected, voltage at the node, magnitude, voltage magnitude at the node, and voltage angle at the node. Notice that we didn't talk about current. Yeah, we didn't talk about current. Now, when and I also said that out of those parameters, there's 2 will be known and 2 unknown. And how are we going to determine those 2? By writing 2 equations for each of the nodes. And what are the 2 equations that we're going to write? We're going to write active power balance equation and reactive power balance equation. Yeah? So when we write the power balance equations, active power balance equation and the reactive power balance equation, of course there's going to be current, isn't it? Power is VI star is the complex power, P plus JQ. So there is going to be current. So how if we are only going to think about P and Q and V and theta, there is no current there, we need to eliminate current. So we can eliminate current from our equations by using this equation that involves the admittance matrix. Current vector is the admittance matrix times the voltage vector. Okay? So that's the motivation behind writing this equation. Okay, so here it is the same equation, I equals YV. Y is the admittance matrix, I is the current vector. Now I've said it a number of times, I is the current injections externally into the network, V is the voltage values at the different nodes, and each of the elements of the admittance matrix, notice that they are Y uppercase Y11, Y11, Y12, etc. And the equation, the middle row, right hand side tells you how to actually obtain those elements in the admittance matrix. So it says the element uppercase Yik is equal to negative lowercase yik because you take the admittance of the line and you negate it. Remember I said that. And then you have when I equal to k, we are looking at the diagonal elements and you simply sum admittances of all the lines. So that's what you see there, right? That's what you see there. And what is I1? I1 is the current that you inject externally into bus I, right, is equal to all the currents that are flowing inside the network, right, all the currents. So that's why you have the summation, k equal to 1 to n, right. So we are thinking about how many nodes in this? We are thinking about n nodes in this network, right. So node 1 connecting to all the nodes. Well, if they are not connected, then obviously the admittance of the line will be 0 if there is no line between two nodes. Right? So you can see the equation I is equal to the sum of k going from 1 to n Yik Vk. So what is that? That's also simply looking at the first equation, I equal to Yv, right? You're looking at the first equation. I is the ith row, right? Ith row in that equation. So you take the ith row of the admittance matrix, ith row of the admittance matrix, and you multiply by the voltage vector, and you have the current II, right? So yeah, right? Is that clear? Is that clear? Yeah. Because it's important that you understand this equation that you're looking at is the ith row of the matrix equation that you're looking there, right? That's it. So you take the ith row of vector matrix Y, multiply by the voltage vector, and you get the ith row of the current vector. And that's that equation there. Okay, so let's look at a network. So that's the network topology on the right. You have two generators, right? Generator connected to bus 1, another generator connected to bus 2. Bus 1 connects to bus 3, and so on. That's how the loads and generators are connected through an electrical network in the middle. And we are given the impedances of the lines. So if you think about bus 1 and bus 2, there is a line connecting bus 1 and bus 2, and the impedance of that line is J0.4. So if the impedance is J0.4, then the admittance is going to be the inverse of that, isn't it? Admittance is the inverse of that. So inverse of J0.04 will be negative J2.4, 2.5. So if I look at this impedance, right, that's Z12, and if I take the inverse of that, then that becomes Y12, which is this value here, right, which is that value there. So I can then take the impedance, this impedance, what is that? That is Z13. If I take the inverse of that, then it will be Y13, right? So the inverse of J.2 is minus phi j. Minus phi j is this value here, y13. Right? Okay. There is no line connecting bus 1 to bus 4. Bus 4 is here. There's nothing connecting bus 1 to bus 4. So this y14, admittance of the line connecting bus 1 to bus 4 is 0. Right? And then here this is 0, right? Ground. So admittance of the line connecting 1 to ground, impedance is J1, admittance is minus J. So Y10 is minus J. Right? So you can then write the admittances of all the other lines, Y20, Y21, Y22, and so on. Right? You can write all those. There is no Y22, right? Lowercase y22, there is no lowercase because a bus needs to connect to another bus. So y20, y21, y23, y24 you can write. Yeah, they are lowercase values. And then how do you get the admittance matrix? Right? So this value here is sum of the admittances connecting bus 1. So it will be y12 and y13. So y12 plus y13 plus y10. Everything. All the lines connecting to bus 1. Right? All the lines connecting to bus 1. So if you sum those, you get minus j 8.5. If you sum all the admittances connecting to bus 2, which is that one, and that one, you will get this value here, y22. You can do the same, y33, y44. Now when I talk about y33, y44, y22, y11, I'm talking about uppercase values because they are the elements in the admittance matrix. Now what is y uppercase y12? Uppercase y12 is the admittance of the line connecting 1 to 2 negated. So this value here negated would be this value here. Right? Okay. So the point I'm trying to make here is that if you know the network structure, you know the impedance values of the lines connecting the different bus bars, you can compute the admittance matrix Y, which is also called Y bus. You can compute that. Okay, so that's all this slide is trying to tell. So that's straightforward. Now let's look at power flows. Now suppose that, suppose I have a bus, right? We'll give it a number for this bus. We'll give it a number. So I can be 1, I can be 2, I can be 3. So let's say it's bus I. So I is just a number. It can be 1, 2, 3, 4, whatever, right? Say that the voltage at this bus is VI, right? It's a complex number, right? Current that is injected externally into this bus is II. Let's say it's II. So I can now say the power that is flowing into this bus is V1 I star. I take this voltage, I take this current, right? So what is the power that is flowing on that line is VI I star. It will be the active power and reactive power flowing in this line into that bus bar. If I ask you what is the current that is flowing in the line that I highlighted in yellow, you would say current that is flowing in that line, right, is II, because we labeled it that way, right? So if I ask you what is the power that is flowing into bus I along that line, you would simply take the voltage at the bus which is VI, multiplied by the complex conjugate of the current in that line, which is II star, and that's the active power and the reactive power that is flowing in the line that I highlighted in yellow into the bus. Right. So then I can think about, this is the network, right? So inside the network, let me draw the lines in red. So those lines connect to different bus bars, right? Different bus bars. So then if I ask you what is the current, if I ask you what is the current that is flowing in here, right? I will label this current as I12. Why would I label it as I12? Because that current is probably flowing from node 1 to node 2, right? And if I label this as I13, it's probably a line that is connecting node 1 to node 3. So the current we can label as I13, makes sense. I could label this current as I14 because that line probably connects to node 1 to node 4. So I can say the current that is flowing is I14, right? So now if I ask you on the top line, what is the current that is flowing? You would say it's I12. One in the middle, you would say I13. The bottom one, you would say I14. But notice that those red lines are inside the network. The blue line is actually external to the network, and you're injecting that current into the node. So I could ask a separate question. I can ask you, in this line, right, in this line that I just highlighted in red, I can ask what's the power that is flowing in that. And you would say, well, it has to be V1 flowing out of it, V1, I12 star. And one in the middle, you would say VI, I13 star. And one below, you would say VI, I14 star. Right? And the active power balance equation and the reactive power balance equation will tell whatever that you inject from externally into the bus has to flow inside the network. Right? So that's the active power balance equation. So you have this equation, and these equations need to make sense to you now. So VI star, right? So if I look at this, so this term needs to make sense to you. What is that? That's the power that you inject into the network. And what are these guys on the right hand side? Well, that's the voltage at the bus bar, VI. And what is this guy here? That's the current that is flowing in all the lines, right? How do I get that? Because I said the ith row here is described by this equation. I just take the ith row of the admittance matrix multiplied by the voltage vector, and that's what I have here. Ith row of the admittance matrix multiplied by the voltage vector is that summation, right? And of course I need to take the conjugate of the current, and they have to be equal. They have to be the same. What you inject has to flow inside the network. So that's the power balance equation for a given node I. Right? So yeah, so that's this equation. That's this equation, power balance equation, active power balance. If I look at the real part, then it's active power balance equation, real part on both sides. If I look at the real part on imaginary part on both sides, that's the reactive power balance equation. Right. All good. So now I kept saying you a number of times that we need to know what different symbols mean. So when I talk about uppercase I11, I'm talking about the 1, 1 element in the admittance matrix. Yeah? We need to know. So the 1, 1 element in the admittance matrix will have a real part, will have an imaginary part. Because it's an admittance, right? It can have a real part and an imaginary part. Voltage at node I will have a magnitude and will have a phase angle. The phase angle is theta I. So we could write like that. Yeah. Or in this fashion, in polar form, has a magnitude of Vi and an angle of theta I. Now, we'll introduce this notation. Theta I minus theta k equal to theta ik. Just we introduce the notation. It's the difference between the angles, theta I and theta k. Okay? So, now, let's substitute this new notation into this equation here. So, we have Vi in polar form is that, has a magnitude, has an angle. We have the summation, which is this guy here, the same summation. Yik is this guy here, has a real part and an imaginary part. So, Yik star is, well, there is this negative sign here because we take the complex conjugate. And then Vk in polar form is that, right? Magnitude Vk and e to the minus j theta k. So then we can just rearrange the terms. We have a magnitude here, those are those two magnitudes. We have this guy here, which is that term there. And then we have cos, we have a plus ej theta I and e minus j theta k. So there is a difference in angles, right? I minus k, theta I minus k. So theta I minus theta k is theta ik. So you have exponential raised to the power j theta ik, which is cos theta ik plus j sin theta ik. Euler's formula. Okay. So we then end up with this equation. Right? We end up with this equation. Si is equal to that. Active power balance equation and reactive power balance equation. If I look at the real part on the right hand side, that's then, and real part on the left hand side, then that's the active power balance equation. If I look at the imaginary parts, that's the reactive power balance equation. Alright, so what do we have? We're still looking at that highlighted yellow equation. Alright, so now I've expanded that a bit. Okay, if I look at the real part on the right hand side of that equation, right? So then I'm looking at, what am I looking at? I'm looking at, remember, notice that I'm multiplying two complex numbers. Gik is a real, multiplied by cos theta ik will give me a real number, minus j bik multiplied by j sin theta ik will give me a real number because you have j squared equals minus 1. So then I can, the real part on the right hand side, so we clearly know what that is, right? Because there are two terms. Gik cos theta ik is going to be a real part. Bik sin theta ik is going to be a real part because j squared is minus 1, right? Multiplied by the magnitude Vi magnitude Vk, you have the summation, and that's the active power balance equation. That's the active power injected into the bus. Now, what is the active power injected into the bus from external sources? Is what is generator injecting and what load is taking out. So suppose that you have a generator and a so this is bus I, right? This is bus I. You have a generator injecting power, right? And then you have a load taking power. So this is PGI, is a generator injecting power. PDI is a load taking power out. So a load and a generator both are connected to this particular bus. Of course, PDI can be 0 if there is no load connected to it. And inside the network, we have all these other lines connecting inside the network. I'm focusing on one particular node. Right? So you have that active power balance equation. And if I look at the imaginary part on both sides, I have this term, the second term, which is the reactive power. Again, I can talk about, instead of active power generation, I can talk about reactive power generation and reactive power consumption from a load. So that will be QGI minus QDI. Yeah. So if a generator is injecting power, that's a positive. If you're taking power out, it's a negative. So notice the sign convention as well. So you got to be clear on the symbols, the notation that we are using. You will be given all these formulas, right? But these formulas will serve you no good if you don't know what it means. If the symbols, if you don't know what the symbols mean, it's not going to help you. It's not going to help you with your understanding. It will not help you to actually answer any questions either. So a clear example is theta ik. What does theta ik mean? We know what theta I means. Theta I means the angle of the voltage at bus I. What is theta k means? Theta k means the voltage angle at bus k. What does theta ik means? So unless you know the notation we use, theta ik is in fact theta I minus theta k, it won't make any sense to you. So that's what I'm telling you. And you also need to know what uppercase Y11 means and what lowercase y12 means. Because you would wonder, what does there is no such thing as lowercase y11 because there is no line connecting bus 1 to bus 1. But there is an element called uppercase y11, right? Which is the 1 element in the admittance matrix. So be clear on the notations and the symbols. Otherwise, it won't help you either to understand or to answer any questions. All right. So this is a picture that I have in my mind, right? So I'd like to think about the poles and wires, the network, the electrical network, right, is something in the middle, right? So is that the Y that is in the middle is the electrical network, right? All the lines that connects the different bus bars. Then I would like to think loads as something external connecting to the network. So you have P4, Q4 external connecting to the network. You have a generator G3 external connecting to the network. I would like to think like that. Yeah. So and same with generator G2 external, right? Connecting to node 2. Notice that. So see the notation that we are using. So the current I2 is the current that is injected, that's I've drawn in purple, is the current that is injected from the generator into node 2. Notice I've marked in purple. And notice I marked in purple V2. That's the voltage at that node, number 2. And notice that next to G2, I've said P2, V2, and Q2 and theta 2. So it's a generator bus. I know the power it injects. I've written it in blue. We know the voltage magnitude, so I've written it in blue, V2. We don't know the angle of the voltage at that node, so theta 2 is in red, and I don't know how much reactive power it's injecting. So it's in red, Q2, right? So notice for the load bus number 4, right? So the current it injects is I4. So it has to be injecting. I4 has to be an injection. Obviously, the load may be drawing, in which case the current will be a negative value. Right? Current will be a negative value. But the sign convention is the current injection is the positive. Right? So that's why I have drawn I4 injecting, even though it's a load. So V4 and theta 2 are unknown. we know how much this load is consuming. We know how much active power and reactive power it will draw. Right? So P2 and Q4 will be known. Yeah? And remember, for external devices, the injection is the positive. If you draw, it's negative. So if the load is consuming power, P4 will obviously have a negative value. Right? And if Q4 is consuming reactive power, it will have a negative value. So convention, the sign convention is important here. So I think this picture gives you a very clear idea of what we are doing, what we are looking at. And the important equations I have written there. So look at generator 1, right? Again, obviously that's a slack bus because we said V and theta are known, V1, theta 1. P and Q are unknown, so I've written it in red, right? So all the bus classifications are there. You can see the slack bus, you can see the generator bus, you can see the load bus. Those are the three types that we're going to have. Now, for each of the nodes, we have to write power balance equation. In other words, from generator 1, generator 2, generator 4, etc., power injection. So let's focus on generator 1. Power injection from generator 1 into the network, what is it? It's going to be V1 I1 star, isn't it? V1 I1 star. So I've written that. What is that equal to? That must equal to the voltage at the bus bar, which is V1, and all the currents that are flowing inside the network. Right? What are all the currents that are flowing inside the network? They are the term in the bracket. Because the admittance matrix multiplied by the voltage vector, the first row. Right? First row of the admittance matrix multiplied by the voltage vector. That's that term in the bracket. Of course, I've taken the conjugate because we want the conjugate of that current. And then we can write that in compact form. I've written that below with a summation. That's just writing it in compact form. The same expression in compact form. So that pretty much is a summary of what we've discussed so far for load flow. What you see in this picture. So if you're able to take a clean sheet of paper and you can draw that and write those equations, I mean those equations will be given to you, but if you can write it, I think then you understand. I like to do that with some of the things that in the past with the transformers and all that, I've said, look, do it like this for three-phase circuit. I said, take a clean sheet of paper, draw this simple page, what is in this simple page, and then you understand. Same thing. I would say if you can do that, then all this talk I've been doing now, up to now, for power flow, we could kind of think that you understood. All right. So where are we at the moment? We have a network. Network has n nodes. For each of the nodes, there are 4 parameters of interest. Out of the 4, you will know 2 for every node, right? And the other 2 you want to determine. So for each node, there are 2 unknowns you want to determine. So in order to determine these 2 unknowns, you would write the active power balance equation and reactive power balance equation. You write 2 equations for each node to determine those 2 unknowns. All right. So you have seen the active power balance equation. You have seen the reactive power balance equation. You have seen that. But for the moment, let's say, okay, let's not worry too much about the exact expression. You have seen the exact expression, right? I mean, if you ask me to write, I mean, I would take a bit of time to write it as myself as well. But we know it's there. That's what I'm trying to say, okay? And in these 2 equations, there are, like for each node, there are 2 unknowns. And we know that. So let's now think from that point. We have 2 equations for each node. For each node, there are 2 unknowns, and we want to solve for these unknowns. We have as many equations as unknowns, and we want to solve for the unknowns. That's where we are at, right? That's where we are at. And these equations are nonlinear equations because it involves power, product of voltage and current. Right? So that's where we are at. So to solve these nonlinear equations, we need some mathematical tool, mathematical technique to solve these equations. Right? We're going to use some existing tool to solve these equations. Right? So let's now keep those equations, the power balance equations aside. We know they are nonlinear, there are some unknowns. Let's keep that aside. We need to have a mathematical tool to solve this. Right? So let's focus on the mathematical tool now. Let's not worry too much about the power balance equation. Keep that aside. We'll come back to that. Let's look at a tool. What is the tool that you need? Right? It's like you have a nail and you want to somehow hammer it into a wall. The tool is the hammer. So let's look at the hammer. Let's look at the tool. So the tool, the mathematical tool that we are going to, one of the tools that we're going to use is the Gauss-Seidel technique to solve nonlinear equations. Yeah, Gauss-Seidel. Gauss-Seidel. Let me Gauss-Seidel. Gauss-Seidel method, technique. That's the mathematical tool to solve nonlinear equations. So let's look at the tool. Let's come back to, after that, once we know the tool, we'll come back to our specific nonlinear equations that we need to solve. Let's look at the tool. So this tool says that if you have a nonlinear equation written like x equals hx, right? X equals hx. If it's written like that, then we can quite easily find the solution to this equation. When I say the solution to this equation, what are we trying to solve for? We're trying to solve for x. Right? That's what when we say we want a solution, we're trying to find the value of x that will satisfy that equation. So to make things a bit more simpler, let's assume that I have an equation like this: x minus root x minus 1 equal to 0. Right? I want to find the value of x that will satisfy that equation. That's a nonlinear equation. I want to find the value of x that will satisfy that equation. So I will write it in the form that is required. The form that is required for to use Gauss-Seidel technique is x equal to hx. So then I can take that and I can say then x must equal root x plus 1. Right? So the function hx is in fact root x plus 1 is the function hx. So I've taken the equation, I've written it in the form that is that I need to write to be able to use the Gauss-Seidel technique. The form that I require is x equal to some function. So if I have this equation x equal to minus root x plus 1, then I could clearly say x must equal root x, x minus root x minus 1 equals 0. Then I can say x must equal root x plus 1. So the function hx has to be root x plus 1. Okay, Gauss-Seidel technique is very simple now. The technique simply say, you guess any value for x. Right? It simply says, guess any value for x. So take x equal to 1, for example. Take any value for x. That is my initial guess. Right? And then I substitute that x, I compute x0. So let's say my initial guess is x0. x0 is, let's say I take anything, like 1. x0 is 1. So then I compute h1, or x0, which is h1. And that value, hx0, which if I choose x0 to be 1, h1, is a better estimate for x than my initial guess. Right? So then I just keep iterating. I take an initial guess, I put that value in h, and the answer that I get out is a better guess, then I take that value, I put it back into H, and I get another answer that's better than the one that I got before, and so on. I keep iterating. Right? I keep iterating until the answer that I get doesn't change that much. And when the answer doesn't change that much, I know the answer has converged. And we have the answer. So you can try this. You can write a little MATLAB program to solve for x, find the value of x that will satisfy that equation. You can start with an initial guess. Start with different initial guesses and see where it leads to, where it ends up with. So that's the technique. So here it is, x equals hx, that's the form you need to write. X upper superscript v, x superscript v is some guess. The next best guess is x superscript v plus 1. So then superscript xv plus 1 is a better value, better guess than x superscript v, and I can continue that process until we find an answer, until the answer converges. So you can see initial guess is 1, then the next best is 2, then the next best after that is 2.4, and then 2.55, 2.59, 2.61, 2.61, 2.61, 2.61, right? It has converged. So 2.61 is the answer. And when the difference is small, you can stop. Between two iterations, the answer doesn't change that much, we can stop. So here is the MATLAB code that you can use to answer that question. And you can use the magnitude to be less than a chosen value, epsilon. Epsilon is a small tolerance. If x is a vector, I mean, here we looked at a single value, but x doesn't need to be a single value, it can be a vector. Then you could use something like a Euclidean norm. If the value Euclidean norm is less than some small tolerance, then we have the answer converged. All right, so I've talked about the two unknowns and the two equations that you can write for each of the nodes, right? I've now talked about, leaving that aside, I've talked about a technique that will allow you to solve it. Yeah? Okay? So now what we need to do is to look at specifically how we're going to solve the nonlinear power balance equation. We know that mathematical tool. We're going to look at how we're going to specifically how we're going to solve the nonlinear equation. So at the beginning of the lecture, I actually forgot to introduce you. Craig Hoskin is an engineer. He has worked for Western Power and Verve and so many companies. So he's sitting in this lecture. He's observing my lecture today. But in a future lecture, he will deliver you some lectures on safety, electrical safety, and some of his engineering experience. So I think it's good for you while you actually, we study all this theory. You also listen to a practicing engineer. Safety is important for electrical engineers. When you go out there, you have to make sure your life is safe, life of other people are safe. Safety is important. So you are going to hear him say electricity can kill you. That's what he told me. That's going to be his first sentence. So he's going to talk to you all in a future lecture. So today he's observing. Craig, you want to say anything? Or?
Yeah. So I was last year, this sort of lecture theatre back in 1981. Was tested. So I did an electrical engineering degree in WA, and I've worked with Alcoa. I've actually tutored here for a couple of years, but I joined the SEC and subsequent version. So I was involved you know what one looks like? Do you know what, in the real world, having done all that study, what someone might actually ask you to do? Well, how do I do that? Well, you've actually done the theory. Now it's a matter of just being able to apply it. So it's useful to actually understand where you can start to at least get an idea of it. So that when they ask you in your first day there, can you do this, or have a look at this, at least you've got some way of thinking about where you might go. So that's what we'd like to do. And power system analysis is a very powerful tool. You tend to find that you're using it, at the higher levels of electrical engineering. It's important to actually understand where these things come from, because what you'll tend to use is a package that will do it all for you. The problem you've got is that you put rubbish in, you get rubbish out. So it's very, very important to understand, to have some tools to make sure that you can trust what you're getting out. So that's the ways I've always looked at it. So it's important to understand how that program will work. The program works basically like this, so that the power flow has to do this. And I think the key thing for engineers is while you may not use this directly, you won't necessarily do a problem where you actually put values in. The important thing is to know why it works or why something happens. That's the important thing for you to be able to actually then, when something goes wrong, you can then go and work out why it went wrong. So that's really, hopefully we'll be able to bring a bit of that to you and do some practical examples and tutorials to say, okay, well, we've learned about this. Look at a real world example that I had to grapple with, and hopefully get some idea that will hopefully reinforce some of the ideas that you're actually getting.
Yep. So thanks, Craig. So we will hear from Craig in some future lectures about safety. Safety is extremely important for you to be aware of because there has been some unfortunate incidents involving UWA graduates, especially because if you're working in substations, you're walking in a very dangerous area with high voltages. So you have to be fully understand the safety, because it can and has taken lives in the past. So it's very important, and this issue was raised by Engineers Australia as well, right? So that's why Craig will do these lectures for you all. Right. Okay. So the stopping criteria for the Gauss-Seidel technique, I said X doesn't need to be a single value. It can be a vector, in which case you could look at the Euclidean norm to present the stopping criteria for the algorithm, or you could simply you use infinity norm or some kind of a norm, right? Because if you're looking at a single value, it's easy. You just look at the absolute value. If the absolute value is less than some number, you can stop. But if you're looking at a vector, then we have to look at a norm, because if you have x1, x2, x3, then you could look at, in a given iteration, you could look at the Euclidean distance, which is x1 squared, x2 squared, x3 squared, square root. And in the next iteration, again, you're going to have new values for x1, x2, x3. You could still look at the new Euclidean norm, and you can look at the difference between the two, and the difference between the two is simply a number. It's not a vector. So that's what this slide is telling you. Okay, so let's see now. You know the Gauss-Seidel technique, the mathematical technique. We know the Gauss-Seidel method can solve nonlinear equations, and the equation needs to be written in the form x equal to something, x equal to a function. And once you have that, then it's pretty trivial how to find the answer. So let's look at the equations that we need to solve for power flow. So this equation that you see at the top, that's the power balance equation. That's what we have, right? SI is equal to SI is the power injection externally, complex power, must equal VI, which is the voltage at bus I multiplied by the current conjugate. Yeah, that's the summation is the currents that are flowing inside the network. Yeah. Okay, so now if I then take the conjugate on both sides, so SI is PI plus JQI, I take the complex conjugate on both sides, so PI plus JQI, the conjugate of that is PI minus JQI, that's the conjugate. So then I need to take the conjugate on the right hand side, so VI becomes the conjugate of VI and the conjugates become the normal variables, because if you take the conjugate twice you go back to what it was originally. So we have that equation, and if we can expand this out, right? If you expand this out, how are you going to expand this out? The summation, notice summation goes from k equal to I to n, right? So when we expand, look at the summation there on the right, it's the same summation except the term k equal to I. So we just, from that summation we have pulled out the term k equal to I, right? So when I pull out the k equal to I, so when k equal to I, you have YII, because k is equal to I, multiplied by VI, right, multiplied by VI star. Yeah, okay. So in the summation there are n terms. I take out the term, I separate out the term when k is equal to I. So in the new summation, I have all the terms except one term, right? So we have this equation now. SI conjugate is equal to PI minus JQI, which is equal to VI star multiplied the summation. Summation is YIIVI plus the rest of the terms, right? So now we can actually write an expression for VI by rearranging terms, because you have VI multiplied by VI conjugate, right? So for this term here, VI multiplied by VI conjugate. So on the left hand side you have PI minus JQI. By rearranging the terms, I can write an expression for VI, right? So it's the same power balance equation. I have written what VI is. Okay? So that's in the form that we require to use the Gauss-Seidel technique, because x has to equal hx. X is what we are solving for. Here we are solving for VI. So I've written VI equal to something. Right? Okay? So I've written VI, see Gauss-Seidel require x equals hx, and I'm solving for x. Here we are solving for VI, so I've written VI equal to something. So it's in that form that we require. So here is the same equation repeated. So you can take an initial guess for VI, substitute in the right hand side, right? Because that's hx, if you like. Substitute, evaluate, that's the answer you get out is a better answer for VI. And I keep doing that. Iterate through to find the answer. So the best way to now look at this is to look at a simple example, right? Now, obviously when we do this, for the slack bus, we don't need to do this, because for the slack bus we know the voltage magnitude and voltage angle. So we won't apply Gauss-Seidel technique to find the voltage magnitude and angle for the slack bus, because that's already known, right? Now let's look at this equation a little bit more. What is on the right hand side? What's on the right hand side? You have PI QI, JQI, right? See, we are trying to solve for voltage at bus I. What is on the right hand side? we have Pi JQi. Suppose that this bus is a load bus. If this bus is a load bus, we know Pi and Qi. You know that already. It's a power injected externally into bus I. Right? So Pi and Qi are known. Vi star is the voltage at bus I. You have an initial guess of that, so you know that as well. Yii, it's the II element in the admittance matrix. So if I is equal to 2, we are looking at the 2 element in the admittance matrix. And rest of the terms are also known. Yik is the Ik element, right? Ik element in the admittance matrix. Vk is the voltages at all the other nodes, right? Because that's a summation. K goes from 1 to n. K is not equal to I. It's the voltage at all the other nodes. So if you have an initial guess of the voltage at bus I and all the other nodes, because we want to solve for the voltages at every node, you have an initial guess. You know everything on the right hand side. I'm assuming that it's a load bus. If it's a load bus, you know Pi and Qi. The power that you inject into that bus is known. Okay, so what is the story? What will you do with it if you actually now dealing with a generator bus? Because with a generator bus, do you know P and do you know Q? You know P, but you don't know Q, isn't it? You don't know Q. But Q in this situation, load bus no problem. Slack bus we don't care because voltage and magnitude and angle we know. We don't write this equation for that. For generator bus, we know P, but we don't know Q, so we don't know what to put in there for Qi. But if we look at this equation, right? This is the power balance equation. The real part is the power injected into that bus. Imaginary part is the reactive power injected into the bus. Right? So if I look at the imaginary part, see the imaginary part? Right? We can calculate that. But of course our calculation is based on our guess of voltages. Yeah? Because we have an initial guess. So we can calculate the reactive power injected into bus I based on our initial guess of the voltages or previous guess of the voltages. Right? Because we have some answers. At the beginning we have an initial random guess, but beyond that we have the answers coming from our iteration. We can calculate that. So that's what we will use when we, for generator bus, when we try to use this equation. Right? That's what we will use. So let's look at an example. So this is an example. Simple example. All right, this is a simple example. Now, manually, you should be able to talk about using, software packages for you to be able to do the load flow. I will talk about that at the end. But simple networks, you should be able to do these things manually, right? And even if you are using a power flow package, you at least know the fundamental understanding, so you know what you're looking at, what you're getting. So this is a simple example. We should be able to do the calculations manually. Let's see how we do this. So we have slack bus, right? We have a load bus. So you have 0.3 for P2, 0.2 for per unit for Q2. You have the transmission line. So what do we start doing? Step one is to create the admittance matrix, because our equations have the elements of the admittance matrix. Pardon me. So Y10 is 0. There is nothing connecting bus 1 to ground. There is no impedance connecting the generator to bus 1. So Y10 is 0. Y12, well, the impedance of the line is 0.1 plus j 0.5. So the admittance is the inverse of that. Inverse of that is that number there, which you can easily calculate, easily find. So y12 we know, y21 is the same number, right? It's the same line we are looking at. y20 is 0, there is nothing connecting bus 2 to ground. So y20 is 0. And that's it. So what is the 1,1 element? 1,1 element is the admittance of all the lines connecting to bus 1, which is the admittance of the line that we see, which is 0.3846 minus j 1.9231, right? 1,1 element. 2 element is going to be the same because it's only one line connecting bus 2. And the off-diagonal terms are, well, admittance of the line connecting 1, 2 negated. So take that value, negate it. So take 1,1 element in this situation, negate that, and that's the 1, 2 element and the 2, 1 element. So given a particular network structure, writing the admittance matrix is something you need to be able to know. I mean, I've talked about it, I explained it. In the previous lecture, I gave the fundamental derivation. Today's lecture, I just told you, without having to do that, how to write it. You need to be able to know that. If you don't know it, well, you need to know it. Now, slack bus, okay, what are the things that we know and what are the things we don't know about the various nodes? That's step 2. Bus 1, we know the angle and the magnitude of voltage. We don't know P and Q. Bus 2, we know P and Q. We don't know the voltage, magnitude, and angle. Right? That's step 2, to know what we know and don't know. So now to use Gauss-Seidel, I said that we're not going to solve for voltage, magnitude, and angle for slack bus. So there is only one other bus that is left for us to figure things out, only bus 2. So we write that equation, that Gauss-Seidel equation, the equation that we derived out of power balance equations for bus 2. We rearranged that and we wrote what V2 is, right? This one here, what you see. Now this equation that you see for V2, again, you don't have to memorize this because this general formula is going to be given to you in a formula sheet. So it's this equation that you see here, right? This will be given to you. So V2, right? I is equal to 2, must equal 1 on Y2, 2, because I is 2, right? I is 2. Minus P2 minus JQ2, right? Because I is equal to 2. Divided by V2 star, okay? Minus summation K equal to 1, K not equal to 2. N is equal to the number of nodes in this equation, N is equal to 2, right? Number of nodes are equal to 2, lowercase n. Yik, Vk. So you have this general equation. You know what little n means in number of nodes. You know what I means. It's the bus I that I'm considering in this case, bus 2, because bus 1 is a slack bus. We don't write equation for that. It's only for bus 2, right? So if you're given this formula, which is the general formula for bus I, and you know that for this particular example, you only need to consider bus 2, right? You've written the admittance matrix, you only need to consider bus 2. So you write the equation for V2. You write this equation, V2 equal to that equation that you see there, right? Yeah. So if you know what the symbols mean, that's what I kept saying at the beginning of this lecture, you can write that equation. Okay. So starting the iteration, we'll make a flat start. So we'll guess, our initial guess is that V2 in our first iteration, right? Our initial guess, it have a magnitude of 1 and angle of 0. That's it. We're just going to guess that. There is no other thing, no other variables that we are looking to solve here, only V2, because V1 we already know. So P2 and Q2, so we know the values of P2 and Q2. Notice that what is P2? P2 was what is P2? P2 was 0.3, Q2 was 0.2, right? Now, notice it's we've drawn, it's consuming 0.3. So the injection is negative 0.3. Remember, I said the injection is what we need to consider here. Injection is negative 0.3. Injection of Q is negative 0.2. So when I write this equation, right? When I write this equation, notice, right? So when I write this equation, notice this. This is P2, is negative 0.3, right? And then we have negative JQ2, right? Q2 is minus 0.2. So with that negative in there becomes plus 0.2. Right? So we have to know the notation, sign convention, what different symbols mean. Then we just simply plug in the values, right? So this value here is Y22 is this guy here, Y22. Yeah. V2 star is still 1 angle 0, because all you do is you conjugate it to negate the angle. If it's 0, then negate it is still 0. And then Y21, we know the value, we put that, V1 is 1 angle 0. That's a better answer than 1 angle 0. Right? Then I substitute that again in that same equation and continue. Yeah? And if I continue several steps, so in the 4th iteration I get that, 5th iteration I get that, the number is not changing that much, and we have found the answer for voltage, magnitude and angle. So now we clearly know the voltage, magnitude and angle at every bus in this network. Okay? Every bus in this network. I know the voltage, magnitude and angle of every bus. I know the voltage, magnitude and angle there. I know the voltage, magnitude and angle there. I've just found that. Okay. Now I ask you the question, if I want to know the power flowing out here, out of bus 1, how can I calculate that? It's the magnitude of the, it's the voltage at bus 1 multiplied by the current that's flowing out. Yeah? What is the current that's flowing out? Voltage difference between bus 1 and bus 2 multiplied by the admittance of that line. Okay? If I ask you what is the power that is flowing in here? I take the voltage at bus 2, right, times the current that is flowing in. What is the current that is flowing in? Voltage at bus 1 minus bus 2 multiplied by the admittance of that line. Yeah? Admittance of the line. Voltage times admittance is the current, right? Yeah? So if I do VI star, I get the power flowing in. So if I have this bus has voltage VI, and I know current flowing out is I1, let's say, I1 star is the current that is the power that is flowing out of that line. Yeah? Right? So if I tell you now what is the power that is flowing in here, complex power, I take the voltage here, which I know now. I want to multiply by the current, of course, conjugate. What is the current that is flowing in here is this voltage here minus this voltage here multiplied by the admittance of the line. Yeah. So now I'll ask you another question. What is the power loss, active power loss and reactive power loss on the line? If I know the complex, if I know the power that is flowing here, if I know the power that is flowing in here, do I know the loss? I know the loss. Just simply take the difference. So what I'm trying to tell you is if you know the voltage, magnitude and angle at every bus, you can do other calculations that you need to know, right? One thing that you need to keep in mind is if I have a voltage at a particular bus, let's say V1, and I know current that is flowing out is I1, and I want to know the power that is flowing through there is V1 I1 star. And we use that idea to actually write our power balance equations and all that. We said externally what you inject must equal what flows inside the network, and we use that idea. Right? And then if I want to know power loss in the line, I know what flows in to the line, what flows out, and take the difference. I got the loss. Right? So when we do power flow analysis, we attempt to find the voltage, magnitude, and angles at every bus. Because once you know that, you can determine everything else. Right? So let's look at a little bit more complicated example. So here is a little program that you can write to do the iteration in MATLAB. You can do that yourself. Right? So let's look at okay, how about we take a short break and then we come back and then we look at this example. So the break will be what, 5-10 minutes?
Oh, maybe rings a bell.
Rings a-
Excel. I'd actually work through a network, and then again, effectively do the same thing. You come up with a new value, which you then use, you actually iterate. And Excel iterates as well. So do they actually just have MATLAB available?
MATLAB is available,
Right.
and MATLAB can actually read Excel files as well.
Yeah, no, I was just thinking, like in the real world, universities and MATLAB and things like that. But I don't know whether people have that available to them when they leave you.
In uni they have student version that they can use, but when they go out, the companies need to have license to use MATLAB. But instead of MATLAB, they use other packages like Power Factory.
Well, yeah, that's right. No, I'm just thinking about just the general bits. Like, that's what I found. I actually found myself starting to use Excel because it was available.
Because the reason that is using MATLAB is because there's the toolboxes for PowerPoint. Because Excel doesn't have that capability.
Oh, no. I actually. So I'm just trying to think. So you're doing fault stuff.
Not yet.
It's not yet. That's the next year. What's the
This is still low.
Yeah,
I have to, after Gauss-Seidel, I have to talk about Newton-Raphson. That will be the workflow.
Yeah.
And then next chapter will be the faults.
You're sort of following
Yeah, yeah, yeah. That's the, I think they don't, they just rely on the notion.
Yeah. It's actually a very good textbook. You sort of,
Yeah,
yeah. Yeah, I mean, I've got, I started looking at things like, best reference book, electrical engineering reference books that you can draw on.
Yeah.
And it actually works quite well because again, it comes back to someone who sat sort of saying, okay, well, from this line, well, I mean, basically the case I had was I had these cables
yeah,
and I had them just separated. And I had to try and work out what the inductance was of the cable.
yeah,
So I actually had to go back to those fundamental formulas
yeah,
about mutual inductance.
yeah,
Forget about that.
yeah,
What I was seeing was I had these three cables that I was supplying power. But what I didn't know when I combed my middle cable was actually taking more current out too. Going, what? And it's to do, you've got red, white, blue. But what's actually happening is because you've got your, they're all 120 degrees apart. What actually happens is the middle cable actually gets, because of the reaction, because of the currents, they're actually sort of semi-negative from the current going that way. So you're actually getting it actually reduces the inductance of the cable. You actually get a higher power flow. Where did this come from? But it's just that simple one of, the two transmission cables, the transmission lines together, and what happens when they're both sending the same current, do they repel or they attract? But it has an effect on the actual current. Crazy things like that comes along and go, well, why is this?
What's the explanation?
What's the explanation?
Yeah, important because once you have your basic knowledge, fundamentally.
Well, you can start to look at it,
Yeah.
and that's why. I actually found that textbook that University were using it, and I
What
actually
is the name of it? Core body?
No,
It'll come to you.
no.
Okay, I think we can start. So, right here we are looking at a bit more complicated example. In the first example, we had 2 bus bars. Well, in this example, we obviously have 4 bus bars. 2 generators connected to 2 bus bars and also 2 loads connected to 2 other bus bars. And we know the network configuration. We know how different bus bars are connected. The lines and the line impedances for each of those lines connecting various bus bars. So what is the first step? First step is to write down the admittance matrix, because when we use our formulas, those elements of the admittance matrix are required. So, when we are looking at the admittance matrix Y, this element here, we need to consider all the lines connecting bus bar 1. So there will be one line here. So we need to consider this line and we need to consider that line. We need to find the admittances of those two lines that are highlighted in red, and we need to add them. So we're looking at line from 1 to 2, and we are also looking at line from 4 to 1 or 1 to 4, same thing. So we need to take this impedance, we need to invert each of those impedance values, and we need to add them. So if you invert each of those impedances and you add them, you will end up with this value here. Right? Then when we look at the off diagonal elements, which is this, this and that, this element here, we are looking at 1, 2 element. So bus 1 connecting bus 2. So we are looking at this element, this line, admittance of that line, and we negate that. And we put in here. So that's that value. Yeah, bus 1 to bus 2. Bus 1 to bus 2. 1, 3 element is bus 1 to bus 3. There is no line connecting bus 1 to bus 3, so this value here is 0. Then 1, 4 element is bus 1 to bus 4. So we look at the admittance of that line. Admittance of that line is the inverse of that. And then we negate that and we put in here. Right? So in fact, if you negate this and you negate that and you add them together, you will get this. Right? Yeah. So you should be able to calculate the admittance matrix. Knowing the network structure, knowing the impedances of the lines, you can calculate the admittance matrix. Yeah? So the first step is to get this admittance matrix. First step is to identify that, Y. And that can be easily done, and you should be able to do that. Right, so next thing is identify what is known and what is not known. Okay, so here we have a swing bus, so we know magnitude of V1, we know angle theta 1. What do we don't know? We don't know P1 and Q1. Load bus, we don't know, we know P1, we know Q1, sorry, P2 and Q2 because it's number 2 we are looking at. We don't know V2 and theta 2. Magnitude of the voltage and angle we don't know. So maybe magnitude we should say like that, magnitude of the voltage. So generator bus, what do we know? We know P3 and we know V3 magnitude. What do we don't know? We don't know theta 3, we don't know Q3. Right? And then with the load bus, we don't know V4, sorry, V1 we know P4, we know Q4. What do we don't know? We don't know V4 magnitude and theta 4. We don't know. So we have identified things we know about the nodes and information that we don't know. For the nodes. Right? We've drawn, so that's okay. What is the step 3 is to write the power balance equations for each of the nodes. Well, except the slack bus. Okay. So what is the equation that will be given to us? So let me take that equation that will be given to us. So we will be given in a formula sheet what we will have. In a formula sheet, we will have this equation, right? So, can someone read out this equation to me, because I can't remember it. You don't have to remember it. So I would ask you to read this out, and also ask you to read this equation out to me as well. Okay? So someone's going to read out this equation to me, yeah, and this equation. Okay? So, because I'm going to write it here and then show how to write the answers. All right. So can you please tell me? Vi equal to Yii, and then Pjqi divided by Vi star minus sum of k equal to something. K equal to 1 to k not equal to I, and then here n, yeah, Yik times Vk. That's it. That's it. Yeah. And Qcal is what? Qical is equal to what? Minus imaginary Vi star k equal to 1 to n Yik Vk, right? So that's one equation. So those two equations will be given to you, right? Okay. So when we look at this, what is n for this particular? Okay. So we can write. Okay. Now let's see how to write. We are looking at node. Yeah. Vk to the power of k. Yeah. So it's these are to the, so on the right hand side, Vk's are to the power of k. On the left hand side, Vi to the power of k plus 1. Okay. So let me go have a look. Yeah. So this is current iteration. Yeah. Current iteration. So if I'm looking at here, so these are everything on the right hand side is current iteration, and then on the left hand side is the new value that you get for the next iteration, right? So I will not write the superscript because we know what it means. Yeah. On the right hand side is the current values, and the left hand side is the new value we get for our future. All right. So Okay. So let's see how, now we are looking at, bus 2, right? Bus 2, V2 we don't know. Theta 2 we don't know. Okay. So we got to write an equation for V2. So we can say V2 must equal, I is 2, right? I is 2. Because I've chosen I to be 2 because I'm looking at bus 2. Yeah? Y22. And then I'm looking at P2 minus JQ2 because I'm looking, I is 2 because I'm looking at bus 2. Yeah? Divided by V2 star. Yeah? Minus. Now, the summation, Yik, K goes from 1 to N. What is N? N is 4. N is the number of buses, which is 4. So when K cannot equal I, so K can't equal 2. K can't equal 2 because I is 2, right? So then we will look at Y11 V1, right? Plus Y, now K can't equal 2, right? So K equal to 1 we considered, K can't equal 2, so the K has to equal 3. So 1, 3. 1, 2 cannot have. We can't do 1, 2. Yeah? K can't equal 2. So V3. Sorry. Okay, let me write it again. In this, I is equal to, in the summation I is equal to 2. So we got to go Y2, right? K is equal to 1, V1. Yeah? The next term is K is equal to 2, but K can't equal 2. So the one after that is K equal to 3. So then Y, right? 2, 3, V3, right? Plus K equal to 4. I is still 2. K equal to 4. Y 2, 4, V4. Right? So you have that. Yeah? So when I looking at bus 2 means I equal to 2. And this formula here says K cannot equal 2. And then we use this equation here to write this equation. Right? So when I write for bus 3, I must equal 3 and K cannot equal 3. So when I'm looking at this equation, I must equal 3, K cannot equal 3. So V3 must equal 1 over Y33. P3 minus JQ3 cal, because Q is not known for bus 3. Right? So we need to calculate it. Q3 is not known, so we need to calculate it. And how do we calculate it? This is how we calculate it. Right? Q3 cal, I is 3, minus imaginary, I is 3, so V3 star, summation K equal to 1 to N, Y 3K Vk. Right? Yeah? So we can write what Q3 cal is, we can write what V3 is. Looking at these equations that will be given to you, we've talked about that, we derived it. So that we know now. So here, when you're looking at bus 4, I must equal 4, K cannot equal 4. So when we are writing this form, using these formulas, we have to make sure I is 4 and K is not equal to 4. So you can write this. So V4 must equal 1 on Y44, P4 minus JQ4, V4 star, and minus the summation K cannot equal 4, K k can equal every other number from 1, 2 and 3, can't equal 4. So we end up with these products for the summation, right? So for this particular network, we have written the relevant equations. For bus 4, Q is known, so we don't need to calculate it. P4 and Q4 are known. We don't need to calculate it. For bus 3, Q3 was not known, so we needed to calculate it. Yeah, we had the equations. So here I have clearly said what needs to be done and how you identify what is the value of I. The constraint k cannot equal I. So when you write down the equation, you write it incorporating the constraint and the relevant bus label. So we have these equations, right? Yeah. So once you have this equation, now it's trivial. We start with a flat start. So V2, V2, V4, we take it as 1 angle 0, right? Now V3, V3 is known, right? V3 is known. So when we do the calculation, we substitute the exact value for that because V3 is known, right? V3 is known. So that's why here in our flat start we have guessed the V2 value, we have guessed the V4 value. Notice that we haven't guessed the V3 value because V3 value is known. So we're going to use the exact value. We're not going to guess it. But the angle we don't know, so we're going to guess the angle. Theta 3 is 0. Right? So here we are choosing V2 magnitude to be 1, V2 angle, so theta 2 angle to be 0, V4 magnitude to be 1, our initial guess, theta 4 to be 0. V3 magnitude we know, we're going to use that. We're not going to guess it. Yeah? Because have a look here. V3 magnitude we know. We know this value. So we don't need to guess it. Right? So this is our flat start. Things that we don't know, we have to make a guess. So now we calculate V2 based on this equation. We plug in the values. Everything on the right hand side is known. We calculate Q3 and we compute V3. We are going to get a magnitude and an angle. However, the magnitude, we reset it to the known value. The angle, we keep it. Yeah? We reset the magnitude. We reset the magnitude to what we know. Yeah? But we carry on with the angle, new angle that we calculate. And then we calculate V4, a new magnitude and a new angle. And we repeat the process. Right? So the key messages, what is the messages? I mean, I'm not showing you how to multiply numbers, that you know. I want to tell you the main idea. The idea is this. You know the general formula, which is an expression for Vi. And what is I in that? I in that is the bus label. Right? Except for the slack bus, every other bus you're going to evaluate this. Yeah? For load buses, P and Q are known. Right? V and theta are unknown. So you need to, both values are needed. The magnitude of the voltage, angle of the voltage are needed. Generator bus, P is known, Q unknown. Q we are going to calculate, but we know the magnitude of the voltage. So in our initial guess, we're not going to guess the magnitude of the voltage there. We're only going to guess the magnitude, only the angle of the generator bus. When we do the calculation, we're going to get a new magnitude and a new angle. But the new magnitude, we're going to reset it to the correct value. The angle, we continue with that angle in our iteration. That's important to understand. Okay? So, how to take the general formula for voltage and QCal QCal becomes important for generator buses because we don't know the Q value, so we need to calculate based on what we know. Yeah? And here are the, you can punch in the numbers and get the answer. So this is what I explained just now. Yeah? So you need to do this question by yourself based on the information that I told you now. Because, that's the way to learn, I think. I explained to you the method, why we do it, the relevant formula, how to use it. So you need to sit and do this question yourself. Because even if I did the question here, it's going to take time. It's not going to make any sense to you because you're just going to see some bunch of numbers and I'm multiplying and dividing the numbers. Yeah? So I explained you the method. So you need to sit down yourself, take some time, do the question. And if you forgot what I just said, well, this is recorded. So listen to it again and do the question. Right? You okay with it? Or you have a question to ask me? Or you're so confused you don't even know the question to ask? What do you think? You want me to re-explain? Or you're okay with it? You're okay with it? Yeah? Okay with it. If you want me to re-explain, I can re-explain. No, fine. That's good. Okay, so that's Gauss seidel. So it's not hard. It's not hard. So you can do the numbers, you can go through the iterations, and then, you can find. So, once you find all the voltages, magnitudes, and the angles for every bus bar, you can then, from bus 1 to bus 2, you can calculate the power that flows from bus 1 to bus 2, which is this guy here. You can calculate the reactive power that flows from bus 1 to bus 2. Right? From bus 1 to bus 2. You can do the same calculations from bus 2 to bus 3. Right? So, like if I'm looking at the line connecting bus 1 and bus 2, I can calculate the power that is flowing out of bus 1, active power flowing out of bus 1, reactive power flowing out of bus 1. I can also calculate the power that is flowing into bus 2. Right? Flowing into bus 2. I can also find the power that is flowing into, reactive power flowing into bus 2. So we know what goes out of bus 1. We know what flows into bus 2. So then I can figure out what's the loss in that line. Active power and reactive power. Right? I can do that. And we can do for all the lines. Bus 2 to bus 3, bus 2 to bus 4, 3 to 4, 4 to 1. We can do all those calculations because we know the voltage, magnitude, and angle at each of those buses. Right? And if I sum all the voltage losses in the lines, well, that's the total loss. I can sum all the losses, reactive power losses in the lines. Well, that's what it is. We can add up all the active power consumed in each of the loads. So you can also do a double check. Active power consumption in all the loads plus the losses, active power losses in the lines is what the generators actually generate if you sum all of them up. So do this double check. Right? So you have a bit of calculation to do at home. You have these numbers here. So calculate all the voltages at every bus. Right? Calculate the power flows out of each bus, power flows into each buses. Calculate the line losses, right? Active power, reactive power. Sum all the load consumptions, active and reactive power. Sum all the generator, active power, reactive power generation. See if all balances out. Because if you've done the calculations right, it should all balance out. Yeah? Right. So that's that's Gauss-Seidel method for you. That's the Gauss-Seidel method. Right? So Gauss-Seidel method is one technique to solve nonlinear equations, and we have looked at how to apply Gauss-Seidel technique to solve the nonlinear power balance equations or power flow equations. That's what we've done. Right? So, for you to appreciate what we discussed today, you need to sit and do some questions, those examples yourself. That's how you will develop further appreciation for these techniques. All right. So, Gauss-Seidel technique is not the only technique that we can use to solve nonlinear equations. We can use another technique. That technique is called Newton-Raphson method. Right? Newton-Raphson method. So what is the Newton-Raphson method? Suppose that I have an equation fx equal to 0. Like a quadratic equation, x squared plus 2x plus 1 equal to 0. So in that case, fx is x squared plus 2x plus whatever I say. Right? Some equation equal to 0, some nonlinear equation equal to 0, fx equal to 0. So how do we solve this? Well, I can take some guesses, right? Well, we took some guesses in the Gauss-Seidel technique as well, and then we refine those guesses. We do the same thing here. We take some guesses and we refine the guesses. So, if my initial guess is x0, and if I substitute x0 in my function, I input x0 into my function, and then I get 0 at the output, then my guess is absolutely correct, isn't it? I just spot on, guessed it correctly. But it is probably unlikely that that's going to be the case. Right? So I make a guess, right? I mean, if it's likely, we will get 100 out of 100 for all the exams, right? Just keep guessing the correct answers. We don't have to turn up to lectures or read anything. So I make a guess, and that doesn't turn out to be 0. Well, that's not the correct answer. But if it's close to 0, if the answer that I if I guess a value for x and I substitute that value in f, and if what I get, the output of the function is close to 0, then we know we may be close to the correct value, solution for x. Okay. So what is Newton-Raphson method? Newton-Raphson method says this. Okay. So if I make a guess, fx0, right? fx0 is not equal to 0. That means x0 is not the answer, right? So I could say x0 plus then delta x, or h delta x or h. H is the same as delta x, right? H is the same as delta x. Must equal the correct value. Let's say the correct value is r. X equal to r is the correct value. So in other words, fr is actually 0. Right? Fr is 0. It's correct value, correct guess for x. So x naught plus delta x must equal r. Right? So delta x we don't know. R we don't know. But we know there is a solution, but we don't know what it is. But x naught we have guessed. So we can say fr equal to 0 or fx plus delta x equal to 0. That's what that means. Fx plus h equal to 0 means h is actually delta x. I could, instead of h, I can say it's delta x. Okay. Now, what I want to do is to write the Taylor series about x0. I can write the Taylor series about x0. Now the Taylor series about x0 is fx0 plus the first derivative evaluated at x0 times delta x plus some higher order terms. We can continue to write. what? It's going to be 1 on 2 factorial, second derivative evaluated at x0 multiplied by delta x plus, can continue like that. Let's not worry about the higher order terms, right? So Taylor series about x0 is fx0 plus the first derivative of f evaluated at x0 multiplied by delta x, right? Now, first derivative of f is the Jacobian of f, right? It's the Jacobian, just give it a name, right? I don't know, just call it Jacobian, yeah? So J, right? So first derivative of f evaluated at x0 is J, Jacobian, multiplied by delta x, right? fx0, we have evaluated f at x0. We were not lucky, it's some epsilon, so we know it's not the answer, right? Must equal to 0, right? F evaluated around x0, like x0 plus delta x is the Taylor series expansion, must equal 0, right? Because we know fx plus delta x is 0. So 0 must equal epsilon plus j times delta x, right? So we have this expression. So delta x is the error, right? In our initial guess, must equal minus epsilon. Epsilon is the output of the function for my initial guess, times the inverse of the Jacobian evaluated at x0. So this is now telling me, if I make an initial guess, how to refine it. Because delta x is a refinement. X plus delta x is my better answer. Right? That's Newton-Raphson technique. That's it. Yeah? That's Newton-Raphson technique. So, yeah, that's Newton-Raphson technique. So if I tell you here, this term here is minus epsilon, right? Because fx0 is epsilon. 0 minus epsilon is minus epsilon, multiplied by the inverse of the Jacobian evaluated at x0 is delta x, which is this. Minus epsilon Jacobian multiplied by Jacobian inverse is delta x. It's actually, I mean, if it's a matrix multiplication, it should be like this, right? Minus epsilon here. Matrix multiplication. Okay? So that's the Newton-Raphson. Delta x is the refinement for the next iteration. All right, so let's say that we want to solve this. Fx equal to x squared minus 2. We know the shape of this curve. Shape of this curve is something like that. What is the answer? Answer also you know. That should be root 2 and that should be minus root 2. And this is minus 2. That's the shape of the curve. Quadratic function. So if you solve this, we must get x equal to root 2. Okay? We know the answer, but assume we don't know. We're going to use the Newton-Raphson technique to actually find the answer. So fx equals x squared minus 2 must equal 0. That's what we are trying to solve. So we compute the Jacobian. Jacobian is the first derivative of x, so which is going to be 2x. That's the J, Jacobian, J equal to that. Our new refined value is the current guess plus delta x. Current value of x plus delta x is the new refined value. What is delta x? Delta x is the Jacobian inverse times the negative of epsilon. In other words, I evaluate f with my current guess, and that's epsilon, right? That's delta x. Yeah. So I can now start with an initial value for x. I can evaluate the Jacobian and take the inverse. Yeah. Multiply by that. XV means the current guess, right? So we can then arrive at delta x. So my initial guess is 1. Delta x that I compute is 0.5. Yeah. So the new value for the next iteration, a better estimate is 1.5. And I take that 1.5 and I compute the new delta x using that formula. What is that formula? Is minus Jacobian inverse times epsilon. Epsilon is the function value with my current guess. Yeah. Jacobian inverse evaluated at my current guess. So, and when I do that, we get that as delta x. So the new value would be 1.5 plus delta x. So we'll get this 1.4 something. And I continue, and 1.41 is the answer, right? Square root 2. So that's the mathematical tool, Newton-Raphson method, for solving nonlinear equations. That requires a Jacobian matrix, computing the Jacobian matrix, and we have an expression in terms of the Jacobian matrix for refining our guess. Delta x is negative J inverse times epsilon. What is epsilon? Epsilon is the function evaluation at my current guess. Right? Does that make sense? Okay. So how do we apply that to Newton? How do we apply that to solve our nonlinear, our power flow equations? How do we do that? How do we do that? Now, for each of the nodes, we have the power balance equations. Yeah? We have an expression for power injected into node I, PIX, active power injected to node I, PIX. So PIX equals to everything on the right hand side. What does everything on the right hand side represent in terms of the network? Those are the power flowing in the lines of the network, right? Yeah, because we are multiplying the voltages by the admittance values and so on, elements of the admittance matrix, Y, IK. Yeah, so I have written an expression for YIK. Right? What is YIK? Where do you find it? What is YIK? It's the IK element of the admittance matrix, right? Uppercase YIK means IK element of the admittance matrix. YIK. And YIK is the IK element of the admittance matrix, and that can be a complex number, right? If it's a complex number, it has a real part and it has an imaginary part. And the real part, we say it's GIK, and the imaginary part, we say BIK. Right? See, you need to be very familiar with the terminology. I said that at the beginning of the lecture. Otherwise, these equations won't make too much sense to you. You have to be familiar with, you don't have to memorize any equation, but you have to be familiar with the notation, what it means. Okay? So YIK, uppercase YIK, what is uppercase YIK? It's the IK element of the admittance matrix. That element is a complex number, which means it has a real part, which we represented by GIK, uppercase. It has an imaginary part, which we represent by uppercase BIK. Okay? So, we have Pix equal to that summation. What are we summing in when we are summing, when we have a summation, what are we summing? Because for each node, right, we have an external power injection. That's what I call Pix. And what are we summing? We are summing all the power flows in the lines in the network. Right? Because the network, I'm thinking of the poles and wires inside that circle that I drew, that I showed you previously in a previous slide. So we have external injection and all the powers flowing inside the network. Yeah? That's what the summation is. Summation is the power flows in each of the lines inside the network. Okay, so you know what theta ik is? Theta ik is theta I minus theta k, and you know what theta I and theta k are. They are the voltage angles at bus I and bus k. And we have Pix. Pix is the reactive power. Right? Reactive power. But the right hand side just shows the reactive power flows in the network. Okay? So, what do we have? What is Pix? It's a power injection into bus I. Power injection into bus I is whatever a generator will inject minus whatever a load will take out. Right? So, you have PGI and PDI. PGI is whatever a generator will inject. PDI is whatever a load will consume that is connected externally to bus I. And now we can write a power balance equation, something is equaling to 0. So we can say Pix minus PGI plus PDI must equal 0. Right? In fact, Pix equals PGI minus PDI. Right? Pix is whatever the power that flows inside the network out of that node in the network must equal to the active power injected by a generator into the bus. So it's PGI minus the power that is taken out of a load, which is minus PDI, must equal Pix. So then I can write this equation Pix minus PGI plus PDI must equal 0. And that is in Newton-Raphson form. We need Fx equal to 0. Same, we can write the same thing for reactive power for bus I. You have Qix minus Qgi plus Qdi must equal to 0. So it's like Fx equal to 0. Right? For each of the buses, we're going to write two equations, and those are the two equations. Now, how many equations we're going to write for Newton-Raphson? Now, this is important. Our objective is to find the voltage magnitude and voltage angle at every bus. Okay? Slack bus, we already know the voltage magnitude and voltage angle. So that's two equations that we don't have to write. So that's what that minus 2 represent in that equation. Okay? There are n nodes. So 2 times n is writing two equations for every node. Why minus 2? Because for slack bus, I don't need to write those two equations. So I subtract that 2, 2n minus 2. For generator buses, say that we have X generator buses. Okay? X generator buses. For those generator buses, I already know the voltage magnitude. So that's an equation that I don't need to write. Right? Because our objective is to find the voltage magnitude and voltage angle. So if I already know the voltage magnitude at a particular bus, I don't need to write an equation. Right? I don't need to write it. So I write 2 less and x less. 2n minus 2 minus x are the equations that I have to write. So for load buses, we are going to write two equations. If you look at this equation, 0 equals Pix minus Pgi plus Pdi. 0 equals Qix minus Qgi plus Qdi. Because P and Q are known, right? How much power a load is consumed, we know. So PGI and PDI, QGI and QDI, we know for load buses. Yeah? We know for load buses because that's how load buses are defined. We know P and Q. Externally injected P and Q for these nodes, we know. That's the definition of load buses. So for load buses, PGI, PDI, QGI, QDI, we know. Right? So PIX, QIX, we can write those using those formulas. You can see the formulas for PIX and QIX. Yeah? And for load buses, we don't know VI and theta I. Yeah? We don't know. They are the unknown variables that we are trying to solve. For slack buses, we are not going to write these two equations. For generator buses, we are going to write only one equation because voltage, magnitude we know. We're only going to write one equation. What is the information we know for generator buses? We know PGI and PDI for generator buses. So that's the only equation we're going to write. We're not going to write this other equation that involves Q because we don't know Q for generator buses. Right? Because for generator buses, we only need to write one equation for Newton-Raphson method. So we know PGI, PDI. We're going to write that. We know the expressions for PIX, which is given here. Right? That's the equation we're going to write. So we need to know which equations we're going to write. We said we're going to write 2n minus 2 minus x equations. Now I have told you what are those equations that we're going to write. For load buses, we're going to write both of these equations that involves 0 for P and Q, right, on the bottom. For generator buses, we only write the equation that relates to P, which equals to 0. For slack buses, we write nothing because V and theta are known for slack bus. All right. So here it is. Newton-Raphson equation. Well, we are saying there are 2n equations here. In fact, there is only going to be 2n minus 2 minus x, many equations, right? Yeah? We're not going to have this many equations. In fact, we are going to only have 2n minus 2 minus x, many equations, right? Yeah? It doesn't matter. This is just generally writing what the equations going to look like, but we know that's how many. What are the equations? Well, we know there is going to be equations that looks at that, right? The power, active power equal to 0, right? What flows in, flows out. We have equations for each of the buses. Reactive power flow in equal to flows out. Unknown variables are the angle of the voltages and the magnitude of the voltages, right? Of course, the slack bus voltage and slack bus voltage magnitude and slack bus angle does not appear there. That's why we have two less equations, two less unknowns. For the generator buses, the voltage magnitude doesn't appear in the unknowns, and that's why we have one less equation, right? One less function. Yeah? So x less functions because there are x generators. There are x generators, right? So, I will continue the discussion on Newton-Raphson in the next lecture. I think we'll stop here for today. I'll continue this in the next lecture because this is an important topic. You need to grasp it properly and well. And we are heading towards the end of the lecture. I don't know the concentration level right now. So, and the maths is getting a bit tougher. So I think this might be a good place to stop. And when I come back, I'll revise a little bit, and then we'll learn about that. Okay?
have your those lecture notes online or something? Or?
Yeah,